Now the next theorem is any tree with at least two vertices has at least two pendant vertices. Recall, pendant vertices are the degree 1. So if you have any tree with at least two vertices, that means G contains at least two vertices. Let G be a tree such that is greater than or equal to 2, at least two vertices. The number of vertices will contain at least two. Let P be the number of pendant vertices let P be the number of pendant vertices in G such that in G with n elements, that will be more with n vertices, that will be more appropriate. G be a tree such that it has at least two vertices and P be the number of vertices, pendant vertices. And we'll enumerate. Let V1, V2, suppose V suffix P be the number of pendant vertices. Let V1, V2, V suffix P be the number of pendant vertices. How many are there? N vertices. The remaining are V P plus 1 and V P plus 2 and so on Vn. These many number, that means Vn minus Vp plus V suffix P plus. These are the number. The remaining, these are of at least degree 2. Is it not? Thus, d of Vi is 1 when 1 less than or equal to I less than or equal to P, the number of pendant vertices, and is equal to at least 2, means greater than or equal to 2 if it is P plus 1 less than or equal to I less than or equal to N. That's what we have. Strictly speaking, N minus P. These are N minus P vertices. Is it not? Up to P vertices they are pendant. So degree 1. The rest are, we are assuming that at least degree 2. By handshake lemma we have we have 2 times E, the number of edges, is equal to summation of dvi equal to 1 to n. So this is again dv1 plus dv2 plus dv suffix p plus so on dvn. Now this graph is a tree. Just now we have proved that if there are n elements in the graph, in the tree, there are n minus 1 edges. So this will be 2 into n minus 1 is equal to. How many are each is? How many are there? This is 1 because pendant means degree 1, degree 1, degree 1. So this is 1 plus 1 plus 1 p times. This is p times. Plus. Each is at least 2. How many are there? N minus p. So 2 into, now dv suffix p plus 1. Here you will have dv p plus 1. So if you look at that, that will be 2n. 2 into, how many are there? N minus p. At least n minus p. So what I have to write here? I have to write greater than or equal to. Because at least 2. So from p plus 1 to n, each is at least 2. So 2 or 3, whatever it may be. 4, whatever it may be. So you will have this. This is equal to p plus 2 n minus p. That is equal to 2n minus p. P, 2n, 2p, p minus 2p is minus p. That will be 2n minus p. Two n minus 1 is greater than or equal to 2n minus p. Let us solve this. This implies, let us say 2n minus 2 is greater than or equal to 2n minus p. This implies p is greater than or equal to 2. What is p? P is the number of pendant vertices. How many pendant vertices are there? At least 2. Has at least 2. Hence the theorem. Now I would like to introduce here another definition. An acyclic graph is called as a forest. An acyclic graph is called a forest. Simply acyclic, there is no connectivity. If it is a connected acyclic graph, it becomes a tree. Now, forest means a node. An acyclic graph is a forest. Removal of an edge. One edge I am talking about. Removal of an edge makes forest into two disjoint trees or into two trees. Enough. That's what I have done in the earlier theorem. A forest of K trees with n vertices has a forest of K trees with n vertices has n minus 1 K edges. Suppose a forest consists of K trees. That means you have removed K edges. You have removed K edges. So, let G be a forest with n vertices and K trees. Forest with n vertices and K trees. Let C1, C2, Ck be k components of G. So there are k components of G. Suppose Ci contains Ni vertices, that is, the Ci will have Ni for each I equal to 1 to k. Thus N1 plus N2 plus Nk, which is the summation of Ni equal to 1 to k, is equal to N. We have that many components of N. Now each component is a tree. Since each Ci is a tree, has exactly Ni minus 1 edges, right? Thus the number of edges in G in the forest is equal to N1 minus 1 plus N2 minus 1 and so on, Nk minus 1 edges, this number of edges. That means N1 plus N2 plus Nk minus k. 1, 1, 1, how many are there? There are k components, it's k. So is equal to, this is N. So the number of edges in k is N minus k edges. Now we recall certain definitions. Already some of them I have done, but I would like to recall. Let G be a connected graph. The definition 1 is the distance of U and V, or distance between U and V. I'm just writing distance between U and V as DUV. Given two vertices, I have already done this. This is the shortest path. The shortest path from U to V. The shortest path means the shortest length. The shortest length. That is DUV. Sometimes we write as also, we write DUV as D suffix UV. Clearly, D is a distance function from V cross V into R union 0 is a distance function. The metric sense. In the metric, D is a metric. So distance function is nothing but a metric. Given U comma V, D of UV is a Australian, including Z. The second one is eccentricity of a vertex U, denoted by DEU. eccentricity of a vertex EU. I want to write down the eccentricity of U or V as, I have to denote with UV. So DUV, which is maximum. So maximum of DUV for U comma V in V is called the eccentricity of the vertex. This is for each vertex. I'm writing EU is maximum DU for V in V, the maximum distance. Let us see the radius. The radius of the graph G denoted by RG. It is the minimum of the eccentricity. Minimum of EV, V belongs to V. Remember that if I am writing a connected graph G, this means G is equal to V comma E, vertex set and edge set. So RG is minimum of EV. And let us see the diameter of G. The diameter of G denoted by dG is the maximum of the eccentricity. The maximum of the eccentricity is the diameter of G. If EV is equal to RG, that means if the eccentricity of the vertex is the radius of the graph, then V is called central. E is called central element. And then the center of G is, center of G denoted by CG is set of all central elements, set of all V in V such that V is a central element. So these are the definitions. Certain definitions I have given already in the previous classes. Now the center and the diameter I'm giving as the center of G is CG. Let us see few examples. Example 1. Look at this. If this is a vertex, what is the degree of V? The degree of V is, it's a distance function. I am defining as a distance function. So this may be 0. What about this? The degree of V is 1. Let us see a simple example with 4 vertices. V1, V2, V3, V4. What is dV1? dV1 means dV1 comma, actually you have to write dV1, V2. V1, V2 is 1, V1, V3 is 2, V1, V4, 1, 2, 3. Now, you want to calculate the distances, right? Now, what I want is eccentricity of V1. Eccentricity of V1 is the maximum distance. What is the maximum distance from V1? Which is V4. So, it is 3. What about V2? V2 is the maximum distance. Here is 1, here is 2. If you count from this side, it is 2. If you count from here, it is 1. So the maximum distance is 2. What about EV3? Maximum distance, now you have to count this side, 1, 2. This, from this side it is 1, this side is 2. So EV3 is 2. What about EV4? 1, 2, 3. Right? What could be the radius? Radius of this graph. Radius of this graph is the minimum of EV. What is the minimum of EV? Among all the other things, there is 2. So the radius of G is 2. What is the diameter of G? The diameter of G is maximum of eccentricity, which is 3. Now, what are the central elements? Central means EV equal to RG. So EV is equal to RG means the central elements are EV is equal to RG, but RG is 2, so EV2 is equal to 2 and EV3 is equal to 2. So V2, V3 has are central elements. So what is the center of G? Center of G is simply V2, V3.
So brainers ఉంటాయి అది ఇగ్నోర్ చేసింది
శబ్దం. Now, let us look at another example. V1, V2, V3, V4, V5, V6, V7, V8. Let us calculate EV1. EV1 means EV1 is maximum distance from V1. So the maximum distance is either up to 7 or up to V8. So 1, 2, 3, 4, 5 or 1, 2, 3, 4, 5. So EV1 is 5. What about EV2? EV2 also will have the same 1, 2, 3, 4, 5. So EV2 is 5. Is it not? And what about EV7? So you are counting farthest distance. So 1, 2, 3, 4, 5. So EV7. Similarly, EV8. So I have the eccentricity of V1, V2, V7 and V8 is 5. Then let us evaluate EV3. Count it. So 1, 2, 3, 4 farthest distance. Similarly, what about 6? 1, 2, 3, 4. So you will have EV6. Will have the same length. EV3 and EV6 have the same length. It's 4. Now we are left over with only I have evaluate EV4. What is EV4? EV4 is if you go this side you will have the length 2. If you go this side 1, 2, 3. So maximum. Eccentricity is a maximum. So EV4 is 3. What about 5? Now, my claim, I'm just leaving it. V4 and V5 are central elements. That means the center of the graph is precisely the elements V4 and V5. You can calculate the radius. The radius will become 3. So I just I mean, you can see V4 and V5 are central elements for this tree, for this graph, connected graph. Now, I have the following theorem. Every tree, following theorem, every tree has a center comprising of either one vertex or adjacent vertices. Or two adjacent vertices. Every tree will have a center. The center is either one vertex or adjacency of vertices, two vertices. The proof goes like this. Let P be a tree with n vertices. That is, V is equal to V1, V2, Vn. With a set of vertices. Let V1, V2, Vn, V suffix P be the pendant vertices in T. So I have V1, V2, Vn. Among this, I have P vertices with degree 1. Now I have to check whether this P vertices will comprise in the center or not, will be in the center or not. Of course, P is where P greater than or equal to 2. That's what, at least two vertices. Now remove all the pendant vertices Now remove all the pendant vertices from T to form a subtree T1. Now again, this is a model. Don't. This is. I want to show only for the visualization of this proof. It's not the proof. It is just only a model. Now I have a pendant vertices with P pendant vertices, and I am removing that. I will have a subtree T1. Now the pendant vertices have the pendant vertices will have the maximum eccentricity. Why? This is a pendant vertex. The degree is 1. Look at this. There is no edge with this. This is V3 has, V1 has only 1, but V3 has 2. So V1 is a pendant vertex. If I take this V1, this the maximum, it will have the maximum eccentricity. What is EV? EV is the maximum of DUV. So distance. If you count from V1 is a degree, so it will be away from everything. So it is farthest. So it will have maximum eccentricity, and a very important point is, and the vertices still remain in T1. Still remain in T1 and do not be, and they don't be in the center. They don't be in the center. This is, look at carefully, the pendant vertices will have the maximum eccentricity and the vertices still remain in T1, because T1 means V1, V2, I am removing the vertices and they don't belong to the center. The vertices of the center. The vertices of the center still remain in T1. Further, we have this. Further, the eccentricity of each vertex. V1, V2, V7, V8 are pendant vertices. Now, the eccentricity of each vertex, I'm talking about, they are, each vertex of T is in T1. And is reduced by 1. Because I'm removing this V1, so it will be reduced by 1. Hence, the eccentricity of hence the vertices of the center of T is having minimum eccentricity. Hence, the vertices of the center of the T has the minimum eccentricity in T1 also. In T1 also. The vertices of the center of T is having minimum eccentricity. That is, thus, center T is equal to center of T1. Now proceeding in this way, we obtain, I'm removing the pendant vertices, so it will have the maximum eccentricity, so centers will remain in T1 even though if I remove the pendant vertices. Hence the center of T and center of T1 are same. Now go on by removing T1, we obtain center T1, center T is equal to center T1 is equal to and so on, center Tm is equal to so on. Hence, each of the center that means vertex of the center, hence each of the center is either one or pair of adjacent vertices. Let us see in this example. Let me remove V1, V2. So I have this graph. There are two cases now. Again I have this V1, V2, V3, V4, V5, V6, V7, V1, V2, V3, V4, V5, V6, V7, V8. Now let us apply this. What are the pendant vertices? V1, V2, V7, V8 are pendant vertices. The proof is over here. Now I am just giving an explanation. V1, V2, V7, V8 are pendant vertices. So remove them. When you remove them, what do you get? The first step, this becomes, I am removing these two, so I will get V3, V4, V5, V6. Because V7, V8 are pendant, degree 1. Now, what are the pendant vertices? Now V3 and V6 are pendant. So I will remove them. If I remove V3, V6, what I will get? I will get only V4, V6. So they are adjacent. Is it done? This is one example. In this example, we have V4, V5 are central, already we have obtained, and now we have two adjacent vertices. Now I would like to see another example. Look at this example. V1, V2, V3, V4, V5, V1, V2, V3, V4, V5, V6. Now I want to remove the pendant vertices. What are the pendant vertices? V1, V2. So V1, V2, also V6, V7. So remove these two. If you remove these two, what is the graph to be left over? You will get V3, V4, V5. Is it not? Now what are the pendant vertices? V3 and V5 are pendant. So remove V3, V5. You will be left over with only one vertex. So the center comprising either one vertex or two adjacent vertices. So I have given two examples. I mean, this is only for an example. I mean, the proof is this. Now we have the following definition. A tree with a distinguished vertex is called a rooted tree. And the distinguished element is called a root. We can have an example on this, a rooted tree. Usually we write the root with a square, not dot. For example, this is a 5-element. Similarly, you can write down, this is a rooted tree, this is the root. This is the root. So 1, 2, 3, 4, 5. You can write down such kind of roots. And let me write down the definition of a special tree. A special tree. A binary tree with at least 3 elements, with at least 3 vertices, is a tree with the degree of root vertex is 2 and all other internal vertices are of degree 3. Look at that carefully. I need, if I want to write down an example for binary tree, I need this. This is the root vertex. Or simply you can write down, when the context is clear, you can write down simply the root. It should have 2. It must be at least 2. If I want to stop here, this is okay, no problem. Look at this. This is root V1, V2, V3, V4, V5. Look at V3. V3 is an internal vertex. The internal vertex will have degree 3. So 1, 2, 3. This is not an internal vertex. This is not an internal vertex. This is not an internal vertex. For internal vertex, the degree is 3. So, usually we write down some of the examples like this. If you look into the chapter, we have the introduction part 0 chapter, chapter 1, chapter 2, chapter 3. You can have like this, chapter 4. In chapter 1, we'll have subsections 1.1, 1.2, 1.3. In 1.1, I can write down again 1.1.1. In this, I can write down 1.2.1, 1.2.1, 1.2.2, like that. Suppose I can write down this as 1.3.1, 1.3.2, 1.3.3, 1.3.4, like this. So this is a binary tree. Remember, the binary tree contains also pendant vertices. This is a pendant vertex in this example because the degree is 1. For this V4, degree is 1, V5 is degree 1. So this is about. Now I have a result or a theorem about the binary tree. Every binary tree has an odd number of vertices. Every binary tree has odd number of vertices. That means there is no binary tree with even number. That's very interesting result. So let us write down the proof. Let T be a binary tree with n vertices and possibly n greater than or equal to 3. Let V equal to V1, V2, Vn be the set of vertices. Suppose, without loss of generality, suppose, I am writing without loss of generality, suppose V1 is a root vertex. Let V2, V3, Vn be the vertices of odd degree. That means either 1 or 3, because I am writing V1 as a root vertex, so by definition root vertex is of degree 2, and I have the rest of the vertices of odd degree. Now we have n minus 1 edges in a binary tree of n vertices. Let us write. We know that summation of dvi I equal to 1 to n is equal to dv1 plus dv2 plus dvn. Look at this carefully. dv1 is of degree 2. This is degree 2. This degree 2. The rest are either 1 or 3. That means they are all odd degrees. But in a graph, the number of odd vertices is even. So this will be even in number. Even in number. So degree of 2 plus even number. Even in number. How many are there? Which is odd. The reason for this is the number of odd degree vertices is even in a graph. So these are even plus 1 odd. So the summation is odd. So hence there are odd number of vertices. Hence n is odd. It's very, very important. So the next theorem is about the number of pendant vertices in a graph, in a tree. So there are n plus 1 by 2 pendant vertices in a binary tree of n vertices. So I have n vertices in a tree, then I must say that there are n plus 1 by 2 pendant vertices. Let us again enumerate. Let V is equal to V1, V2, Vn be the set of vertices. So there are n vertices and clearly n greater than or equal to 3. That's our definition, binary tree. By previous theorem, n is odd. Now, what are the possibilities of the tree, binary tree, about the degree? There is a degree 1, degree 2, degree 3. So there are pendant vertices, internal vertices, and root vertex. So let V1 be a root vertex. Hence, let V1 be a root vertex. Let V1, V2, Vm be the number of pendant vertices. Means degree 1. I have a root vertex from V2 to Vm. I should be careful about this. Let V be a root vertex and V1 to Vm be the number of pendant vertices. Thus, there is a root vertex, one root vertex of degree 2 and n minus m internal vertices of degree 3. So I have a root vertex and I have m internal vertices, so each is of degree 3. Now I have to evaluate m. The m must be n plus 1 by 2. That's what our claim. So if I want to show n minus m is the number of internal vertices, if I want to show that m is n plus 1 by 2, I will consider these two. Thus, n minus 1 is equal to, what is n minus 1? This is the number of edges in T, in the graph T, in the binary tree. Because if there are n elements, you will have n minus 1 edges. Now I have to count these number of edges. Now, how I will count it? I will count like this. There are n minus m, so I have to remove 1 because there is one root vertex. There are n minus m minus 1 edges with degree 3. If there are n minus m vertices, the number of edges will be n minus m minus 1. If there are n vertices, n minus 1 is the number of edges in a tree. So 3 into n minus m plus 1. How many pendant vertices are there? M. So I have to write down 1 into m because degree is 1 with m vertices plus 1 vertex. What is that? Root vertex, degree 2. But I am counting this in a tree. We have to count the vertex, we have to count the edge only once. So I have to divide by 2. So these are number of edges, right? So let us solve this. This implies, if I multiply by this, I will get 2n minus 2 is equal to 3n minus 3m minus 3 plus m plus 2. Solve for m. I need m. So 2n minus 3m is minus n minus 2. This is minus 3 plus 2 is minus 1. So if it comes here, it will become plus minus 3m plus m is minus 2m. So this implies minus n minus 2, this is minus n minus 1 which is equal to minus 2m. Cancel throughout, take out minus, so you'll get 2m equal to n plus 1. So m is equal to n plus 1 by 2. What is m? The number of pendant vertices. So there are n plus 1 by 2 pendant vertices. Thus there are n plus 1 by 2 pendant vertices. Now, at another interesting about this is the theorem. At another theorem, there are 2 power nc2. There are 2 power nc2 labeled graphs. There are 2 power nc2 labeled graphs with n vertices. There are 2 power nc2 labeled graphs. Let us try this one. The proof is in any simple graph, with n vertices, will have at most nc2 edges. That is n into n minus 1 by 2. Whatever the graph n with n elements, you will have nc2 edges. Now let us continue with this. Now for q is equal to 0, 1, 2 to nc2. I'm looking at the number of edges. The number of possible for q, the number of possible edges. The number of possible edges is same as, look at carefully. I'm looking at for q equal to 0 with 1 edge, 0 edge, 1 edge, 2 edge, nc2 edges. I'm looking at this. Is same as selecting. I'm selecting it. It says selection. Selecting q pairs out of nc2. I have nc2. I'm selecting a q pairs. So this is same as nc2 q nc2 c q. I'm selecting q out of nc2. This is same as this. Thus, the number of labeled graphs. I'm looking at the number of labeled graphs of n vertices. On n vertices is the summation nc2 c q. Q runs from 0 to nc2 because I have already chosen the edges. How do you calculate this? Simple, it's binomial. So this will be 1 plus 1 whole power nc2, which is equal to 2 power nc2. So there are 2 power NC2 labeled graphs on n vertices. Let us see a small example with 3 vertices. N is equal to 3 labeled graphs. How many labeled graphs are there? We'll see. So obviously you have to get 2 power, n is 3C2. So 2 power 3. That means you have to get 8. Obviously the first one is this one, 1. First label. The second label is 1, 2. 1, 2, 3. 1, 2. 3 separate. Make it isolated. Join 2, 3. This is separated. 1 is isolated. And then 1, 3. 2 is isolated, which is. Now I have to write down 2 at a time. 1, 2, 3. Then 2, 3, 1. The 7th one is 1, 2, 2, 3, 3, 1. Then again you will have the 1, 2, 3. The final one is the number of labeled is complete. You will get a triangle. 1, 2, 3. So there are 8 in number for n equal to 3. This is a very interesting theorem. And now this is, even though it's the proof is beyond your, not here, but you can search for it. So there are n power. Now I'm talking about the particular graph. N power n minus 2 labeled graphs, labeled trees with n vertices. And the proof is just simply exercise.